Now we are welcoming George Weber from King's College London. George will give us an overview on his work on non-overfitting objective for PET image reconstruction.
Hi everyone, I'm George. I'm a PhD student here at King's College London, and today I'll be talking to you about my recent work on a non-overfitting objective for PET image reconstruction. So the PET image reconstruction task, as it were, is an inverse problem. Hopefully everyone in this room is familiar, where we have some measured tomographic sinogram bins. These are lines of response that have Poisson noise attached to them, and we're looking to reconstruct a high-quality PET image. And to do this, we specify a reconstruction algorithm, of course, where we have to balance concerns around data fidelity, so how well is our image explaining the measurements, and also regularization. So most of the talks today so far have focused on regularization, and that's where lots of the literature is at. But I'm going to be talking about my new approach for how we can actually measure the fidelity of an image. And so usually you would do this with a likelihood. But the likelihood has a few issues. So at its core, the maximum likelihood estimate is not the ground truth. And so if we keep iterating an algorithm like MLEM, we'll eventually end up at a noisy maximum likelihood estimate. So we've overfitted to noise. And as a result, there's no necessarily ideal data consistency level. Of course, on a task-by-task basis, we can find a good data consistency level. It works very well generally. But when we want to introduce some regularization, we might have some conflict. So for example, in the kernel method, we might want a kernel that imposes some nice structure, but it also has to do this task of dampening down noise. And so what we'd like in this objective that doesn't overfit to noise. And so I'm going to propose a distributional consistency, so DC loss, for PET image reconstruction and some other tasks that has the following benefits. So it doesn't overfit to measurement noise. It defines a principled level of data fidelity, where we have 0 DC loss being the best you can do. And it also works with many standard optimizers and regularizers. So to see how we're going to build such an object, let's go back to how we can build our standard likelihood. So in the likelihood case, we have an image estimate, and we have some measured data, a prompt sinogram. And the first step is that we apply our forward model to the image estimate to get our forward model of the sinogram means, and then we apply the Poisson log likelihood formula, and that's going to give us an update direction that pushes our measured means towards our measurements. So if we look at the 1D case, if we have here a Poisson distribution with a mean of 3, and we're looking to explain some measurement that was 15 counts, if our Poisson mean, we'd model it as being 3, then this is actually very, very unlikely that we would see 15 counts. We can calculate what percentile of the possible measurements we'd be in, and we'd be in essentially the 100th percentile. It's very unlikely to see such a thing. So what we do when we optimize is we push our mean Q closer towards our measurement, and this means then that we're much more likely to see a measurement like that, and we say that that's adequately explaining the data. And in the one-dimensional case, this is about as good as we can do. The maximum likelihood estimate is just kind of all we can do in one dimension. But if we have thousands of measurements in a Poisson noisy sinogram that we know are independent, and we see all of these percentile values, if they're all close to about 50% or so, that's vanishingly unlikely. We're just overfitting to the data at that point. And so what we'd expect actually is a much more uniform distribution of these percentile values. So how can we use this observation to help us build a different criteria? So as before, we can apply our forward model to our image estimate to get our forward modeled sinogram. And then we can calculate these percentile values that we've just seen per sinogram bin. So for each of the values in this little sinogram, we've just taken our current model of the mean as well as the measurement. We've calculated this percentile value. We then can aggregate these percentile values into a histogram like we see here. And this histogram is really useful about telling us how well calibrated our image estimate is. So to see this, we can run an MLEM simulation, which we'll do now. And when we're getting a uniform histogram where all of these histogram bins are around the 1 mark, then that means that we're actually explaining the data adequately well. And so what that means maybe more intuitively is that 70%, so if we have 70% of our measured realizations are appearing to be 70% or less as a percentile, then we're explaining the data equally well as the ground truth. So maybe just to reiterate that, if that histogram is flat, our image estimate is explaining the data as well as the ground truth is. So if we run an MLEM iteration, so we can start with a poor image estimate, and that image estimate would correspond to this histogram here on the left hand, my left, your right-hand side. And we can see at the moment that we've got a big spike around the 0th percentile and around the 100th percentile, and that's meaning that lots of our measurements in the sinogram are being very poorly explained. So the associated measured modeled mean in that sinogram bin is way too small or way too large. As we run the MLEM algorithm, we can see that this histogram approaches near uniformity at about the best point for our MLEM image. And then as we keep iterating, we see that the proportion of bins that are in the kind of near the 50th percentile or so in the histogram gets higher and higher. And this corresponds with the point at which our image estimate begins overfitting to noise. It's not too extreme here, but if you have a smaller voxel size, it makes it much easier to overfit to noise, and you see a much, much more pronounced peak as well in this histogram. So how can we use these observations and then build a loss that is not only going to get us to uniformity, but then is going to keep us there on the histogram? So the obvious thing to do is to penalize the histogram's non-uniformity directly. And then that can be our loss function. And so we'll have a loss where we're calculating these percentile values across the sinogram, and we're comparing that with a theoretical uniform distribution. Then, if we have a low DC loss, then our measurements have been well explained by the image estimate and the forward model. And if we have a very, very low DC loss that's near 0, we can say that our image is explaining the measurement data equally as well as the ground truth is. It may be true that multiple images could have a low DC loss. There might be some non-uniqueness here, particularly with lower stats. But then we can use regularization to choose between these minimizers of the DC loss rather than regularization trying to dampen down on noise spikes and fight against it that way. Some mathematical detail. So we use the Wasserstein 1 distance to actually calculate this difference between the histogram and uniformity. And we also work in the logit space rather than in standard space, analogously to how we minimize the log likelihood rather than the likelihood. And that gives us gradient stability. So a few results. So you can see here that we have a synthetic data setup where we're doing likelihood minimization, either with just the Adam operator or the MLEM algorithm. And in both of these cases, when we do lots of iterations, we eventually get Thank you, Andrew. Yeah, for my 10-minute warning. It's more dramatic than I've had at previous conferences. Okay, yeah, so maybe the flagship result then is that when we optimize our DC loss with the Adam optimizer, instead we reach a good image and then we stay there. So once we get to something that's adequately explaining the data, we're not getting really much more gradient signal from our data fidelity loss. When we actually look at plotting the DC loss over time, we see that in blue we converge towards something that has near 0 DC loss, and then we stay there, whereas the other methods that are doing likelihood minimization have a dip, and then they rise as they begin overfitting the noise instead. And this broadly lines up with what's happening with the normalized root mean squared error, where with our DC loss we reach kind of its best error, and then we flatline there. Note actually that MLEM is achieving a slightly better error than DC loss here. So we're not claiming that DC loss is some magical pill that's going to give you better error necessarily by itself. But what it is doing is it's stabilizing those late iterations at kind of the best point that it's reached. What we need is we need regularization or a different optimization trajectory to get to a different, better estimate that has lower error. So we tried out introducing some handcrafted regularization into this setup as well, with an edge-preserving total variation prior. And you can see that these points on this graph here represent the kind of converged solution at different regularization penalty weights. And you can see that in our case, we're getting lower error than the likelihood-based objective. And the reason for this, we think, is that when you're minimizing this penalized version of the problem with a likelihood, your regularizer has to do two things. It has to dampen down the noise spikes, and it has to impose favorable structure. Whereas in the DC case, you don't need to minimize those noise spikes. They're not really appearing. You can just focus on getting some nice structure into the image. So we've started looking into this with real data as well, with real 3D PET data, and we have qualitatively some evidence that the DC loss seems to be kind of working here. It's still under investigation as part of my PhD. Something else that we can say is that the DC loss is measuring how well your image estimate and your forward model is explaining the process. So if your forward model is off, then the DC loss might flag that up and say that you're not adequately explaining the data as well. So hopefully more results to come in this direction. We can also generalize this construction to other inverse problem setups. So the assumptions we need are that we have many measurements, enough that the central limit theorem can apply, and then we have a known noise model per measurement, and we have independent noise per measurement. And then we just do the same thing as before. We calculate these percentile values and do the Wasserstein 1 distance. So in particular, we've tried this out with Gaussian noise, again in a simulated setup. So deep image prior, as people have already mentioned this morning, can be used to do image denoising. And so here we took an image, added some Gaussian noise, and then looked at whether the deep image prior approach could reconstruct a good image from those noisy measurements.